Hi class, we are on to the next section, the next chapter, really chapter 3.1. Chapter 3, we're going to talk about the derivative, and this is really our bridging chapter. It's only 3 sections long for bridging our ideas of a limit with that of the derivative. So we haven't really talked about the derivative yet. We have informally, so now we're going to really start to lay the groundwork, and then the next section will formally talk about what a derivative is. So we're not actually we're gonna talk about the derivative, but we're not gonna talk about the derivative right now, if that makes any sense. So right now we're gonna talk about limits, right? So if you've seen before, we're doing a lot of what's called the difference quotient, right? So really what we're gonna do now is we're gonna talk about the difference quotient and using that with limits, right? So the difference quotient is pretty much our average rate of change, right? So we're gonna talk about how that and our limits come together to form our idea of what's called the derivative. So let's start off with the average rate of change. Okay, so just a reminder that for a function, the average rate of change from an input of x to an input of b is the difference in the outputs over the difference in the inputs. So remember, this is pretty much the same thing as slope, right? It's the slope of a secant line for a function. So if I took any 2 points on a function and I drew a line between them, the average rate of change is the slope of the line that connects them. So if we take a small little animation here, right? So let's say that this is a parabola, and I connect 2 points on my parabola with a line, one of those being an input of A, the other being an input of B. I can then look at the outputs of A and the outputs of B, okay? And the slope of this line that is connecting those 2 points is my average rate of change. Oops. Okay. So what we're going to do now is, instead of looking at this as outputs over inputs, we know that this is a distance, right? This is my vertical distance, f of b minus f of a, and b minus a is my horizontal distance. So instead of looking at this as from B to A, let's just call this a distance of h. So I'm at a value of A, and B is a distance of h away from A. Okay, so again, h is just the distance between these two values. So if I actually found the value of B minus A, let's say it was like 5 minus 1, my h would be 4. Right, so h is just the value of the distance between these two values. Okay, so if I had to rewrite this, instead of writing it as a and b, I'm going to look at this in terms of the distance between them, h. Okay, so what we're going to start doing is we're going to rename this. So instead of a and b, this is going to be a and then a value that is h away from a. Okay, so if I kind of manipulate this a little bit, b is the same thing as a plus h, right? I have a, and then this is a plus a distance of h. So my b gets replaced with a plus h. So when I plug that in everywhere, my equation, f of b minus f of a over b minus a, well, I know b minus a is h, right? Because b is a distance of h away. So this distance is h. And b is no longer b, but a plus a distance of h. Okay, a plus my distance of h will get me to b. So this is what this looks like when I replace it. You've probably seen this in this class already, but didn't know exactly what it was, or maybe you have if you've seen some calculus stuff before. But this is our difference quotient, right? We call this the average rate of change. We call this a difference quotient. It's pretty much the same thing. We're just has a slightly different verbiage for it. Okay, so now what we're talking about is we've basically gotten rid of b. There's no more b's. There's no more my point A and then the second point B here. Now all I'm talking about is A, because what's going to happen is I'm going to make A fixed, meaning it's not going to move. And I want to know what happens as I move this point B around my curve, right? So as I move B around my curve, this distance h changes. So it doesn't make sense to call this B anymore, because now since A is fixed, it's the only thing that's constant, no longer moving. So I'm going to talk about A and this point as it moves away and closer to 8 by referring to it as A plus the distance that point is away from my fixed point. So what I've done now is I've turned everything into A. I have A, I have the distance away from A, and I have the output when I'm a distance away from A. Okay. So now everything looks like this. I have A, I'm a distance away from A. This is my output at A, which stays fixed. This point, this input and output do not move. But as I move, as my H value changes, my output value will change as well. So I'm going to just really talk about it as what's happening to the distance away from A. So as H gets bigger or smaller, this output is going to move along this curve, but A stays fixed. So again, I'm really just rewriting everything in terms of the point that's not moving since everything else is moving. Okay. So this line is going to change, right? As my point moves along my curve, my slope here will get more and more positive or become more and more negative because it gets stretched out and compressed as I move along this curve, right? This line, I said it before, is called the secant line. Okay, now I know you know secant from your studies of trigonometry. There is a relationship there, just like there is for the tangent function and what we call a tangent line. So the secant line is basically any line that intersects a curve at 2 points. Now, if this was like, let's say this was a sine curve, and I drew this line, it would be possible that this line cuts through my curve at more than 2 places. And that's fine, because I'm really only looking at 2 points at a time. It would still be called a secant line. Okay? So again, it's a line that intersects the curve at 2 points. So this is what's happening. Okay, so instead of now drawing it as just a chord basically ends, it goes from one point to the next. We're going to draw it as a line, right? So it extends in both directions forever. I have my A and F of A, my fixed point, and now I have my point that is a distance away from A and its output. Okay, so now we have everything set up for our exploration, right? As I said, we're going to move this point left and right, so like away and towards our point. Really what we want to do is not go away from our point. We want to move it close to our point. So we want to start to move this point close to A, meaning that H is going to get small. It's going to go to 0. I want to really see what happens when this goes to 0 and the points meet up at one point. So what's going to happen is that my point is the point on the curve is going to get closer and closer and closer, and this secant line is going to have a greater and greater and greater slope. Okay, and I want to see what happens when I go all the way to 0. I can't go all the way to 0 because I'm no longer a secant line at that point. And if I go to 0, well, look what happens. My denominator becomes 0. My function becomes undefined, right? So we're going to look at the limit as h goes to 0. Since I can't actually just plug in 0, I can take the limit and see what happens as I get closer and closer and closer. So, here we go. So, let's give these points some names. So, my fixed point, A, F of A, I'm going to call it P. And the point that I'm going to move around my curve, I'm going to call it Q. So, this will be P and this will be Q. Okay. So, A is the fixed point. Q will move, so I'm no longer going to write it as, A plus H as the input and F of A plus H as the output, since it's going to continue to move. And what I'm going to do is I'm going to bring it along my curve closer and closer to Q. So you see here, it's under the vertex. Here I'm at the vertex. Here I'm just past the vertex. So you see how the slope is changing as well. And the points P and Q are moving closer together. You can see that if I were to draw the inputs, that the points are moving closer together, right? So I'm going to keep doing this until H goes to 0, which would mean that P and Q are the same point. And I'm no longer a secant line, but I am what's called a tangent line. So I only intersect my function now at one point. So P equals Q. Okay. So what was my average rate of change? I've now took the limit of as that distance between the 2 points got smaller and smaller and smaller. And the average rate of change turns into what's called the instantaneous rate of change. The instantaneous rate of change is the same thing as the slope of the tangent line. So the tangent line only touches our graph at one point. Okay, there's only one point of intersection. So the slope of the tangent line gives us the instantaneous rate of change at that point P. Right. So my instantaneous rate of change at a point is the same thing as the limit as h goes to 0 of the difference quotient. So me plugging in a plus h into my function, subtracting f of a, right, my output for the fixed point, divided by h. Okay, so this is very, very important. This is our idea for the remainder of the course. This single slide here is the idea for all of Calculus 1. Okay, so let's go to Desmos real quick and let's play around with the graph and animation so you can see this with moving parts rather than, various still images. So here we have a function, another quadratic because they're easy. Here we have a secant line. We're going to hold one point fixed, and what's going to happen is that this line here will move along my curve. Okay, so you can see that the input values here will change, obviously. I don't have a slider for that, but it'll move as well as we get closer and closer to our point. And as we move to a tangent line, we have just a single line there. Okay. So here, if we draw this as an animation. Okay, until we get to a single point. But a quick update to notate our point A, which in this case is -1, and our a plus h, so that we can really see what's happening here, right? So we see that the a plus h is moving to a. So the distance between them is getting smaller and smaller and smaller until there is no distance. And then our secant line, which intersects twice, will then intersect at only one point, and we have a tangent line, right? So the slope of this tangent line is what's important to us, right? Because the slope of the secant line is our average rate of change. The slope of the tangent line is the instantaneous rate of change. It's how my curve is changing at this exact moment in time, right? So not from 1 second to 2 seconds, right? Not over an interval, but right now. So that's what we're interested in. That is the idea for Calculus 1. So let's go ahead and do an example. So let our function be 2 over x plus 2. We want to find the instantaneous rate of change at x equals 3. So the instantaneous rate of change is the limit as h goes to 0 of this difference quotient. Okay. Now my point of interest is 3, right? That's my fixed point. So I want to know what happens as I get closer and closer and closer to 3. So I'll plug in 3 to my function, and I'll plug in 3 plus h to my function. I do not have a value for h. H is the thing that is changing, that is moving, that I'm taking the limit of. So I'm not plugging in values here. H is in this case, the variable that's changing as I move. Okay, so I'm plugging in a fixed point for my function. So the limit as h goes to 0 of f of a plus h means that everywhere I see x, I replace 3 plus h, my a plus h, right? A is 3 in this case. So I have 2 over 3 plus h plus 2. I'm going to subtract from that f of a. Remember, 3 is what my a is. So I'm going to plug in 3 everywhere. So 2 over 3 plus 2 over h. Okay, so that's what this is going to look like. And so as I do my calculations, I'm just going to simplify everything. So we've gone over limits quite a bit. I can't take the limit as h goes to 0 as it is because I'll get 0 in the denominator, which is not okay. So I got to do a little bit of finessing, right? So I'm going to simplify this numerator. This is a complex fraction, so I can either multiply top and bottom by whatever the common multiple is, the least common multiple, or I can simplify just the numerator. It's really up to us. So here I'm going to start to simplify. I'm going to add the 3 plus 2. I know 3 plus 2 is 5. If I want to make a common denominator, I can do that. Or I can clear the common fractions, which is what I did here. I multiplied top and bottom times 5 times 5 plus h, because that is the common denominator for this term. So top and bottom, I multiply times 5 plus h. That's why this is 5h, 5 plus h. Here, if I multiply this times 5 plus h, I'm going to get a 10 because the 5 plus h cancels. Here, my 5 is going to cancel, and I'll be left with 2 times 5 plus h. So that's how I got this. There are other ways to simplify this. You'll always come to the right answer as long as you're doing the right work, right? So let's continue to simplify. I'm going to distribute this 2. So I'll end up with a 10 minus 2h. Okay. The 2 10s will cancel, and so will the h's. I'll be left with negative 2h, 5h, 5 plus h. So those h's will cancel. I'm left with negative 2 over 5, 5 plus h in the denominator. Now I am continuous at h equals 0, so I can just plug in 0 for h, and I'll get negative 2 over 25. So my instantaneous rate of change at x equals 3 for this function is negative 2 over 25. So that is the slope of the tangent line. That is how fast my curve is changing at that exact moment. Okay, so at x equals 3, my function is changing at a rate of negative 2 over 25, which means my function is decreasing at this point. Okay, at x equals 3, I'm changing in the negative direction, so I'm decreasing in value. It also means that the slope of the tangent line is negative 2 over 25. Okay, so let's say that I want to find the equation of the tangent line, right? We've been talking about the tangent line. We've been talking about the instantaneous rate of change. I know that instantaneous rate of change is the slope of the tangent line. But what if I want to find the equation for the tangent line? This is a really big deal in this class. So what I'm going to do is, I know that I have a point on my function. I know that at that point in my function, that is when the tangent line is also connected to that point. So I also have a point for my tangent line. So remember, for a line, all you need is a point and a slope. Okay, if I have the slope and a point for that line, I can draw that line. So we already know what the slope is negative 2 over 25. The only thing I would need is to be a point on my line in order to finish finding out what the equation for that tangent line is. So I do have a point. It's the point of intersection. Because remember, I'm interested in what's happening at this point. The tangent line has one point of contact in common with your function. So whatever this point is, in this case 3, if I plug that into my function, it will also be the same output for my tangent line. Okay. So I'm going to find f of 3. I already know what f of 3 is actually because I did it up here. I know it's 2 over 5. But let's do this anyways. It's 2/5. So my tangent line then to this equation has a slope of negative 2 over 25. And it satisfies the point 3 and 2/5. So I just use these two pieces of information to find the equation of a line. So y equals mx plus b. I plug in my y equals mx plus b. Clear my denominator so I can multiply everything by 25. And then just solve for b, right? So 10 and 6. So this will be 16 is 25b. Solve for b, you get 16 over 25. So the tangent line to my equation, f of x is 2 over x plus 3 at x equals 3 is the line y equals negative 2 over 25x plus 16 over 25. So if this is my function, okay, let's look what's happening. At x equals 3, my function is, in fact, decreasing because its rate of change is negative, right? I'm changing in a negative fashion. I'm getting smaller. Negative rate of change, negative instantaneous rate of change, right? So if I look at that point, this is my point 3 and 2/5. I know we can't see that it's 2/5, but this is 3 and 2/5. And the equation for the tangent line has a negative slope, okay? And it only touches my graph in one point. It never touches my graph again, okay? So that is the tangent line to an equation, to a function at a point.